but the bath that they share is common. Right? So that introduces a coupling or a self-consistency requirement between the two. Okay? I mean, that is physically explaining why it comes about.
Could you explain why the homogeneous model cannot explain any model cannot explain the certain feature of this experiment? Is there any some rule or some?
No, there's no exact sum rule that we can suggest, but what we can say is that, okay, I mean, I should modify to some extent. I have not seen any calculation from a homogeneous model that can simulate this. We have some qualitative physical statement to make why such a thing cannot come out of homogeneous, but it's not a rigorous theoretical proof. So I cannot deny the possibility that there's a very strange homogeneous model that will explain this. Okay? But I personally do not believe that would happen, simply because there is, at least in the half-filling case, there's electron hole symmetry. Okay? Of course, we are talking about a highly degenerate case. So that is different. But if you allow to discuss in terms of a half-fill case or a single degenerate problem, then there's no homogeneous model that can do it. Simply because there's an electron hole symmetry, which means the correlation effect that shows up in the occupied part must show up with the same strength in the unoccupied part. Okay? So, that is a rigorous statement. But here we have, of course, high degree of degeneracy. Okay? So degeneracy of 5 because we are talking about D. So the statement can get modified. When you do take into account degeneracy and do exact calculations, people have done exact calculations with small clusters, you find again that very intense satellites show up in the occupied part, in the unoccupied part, so in the unoccupied part also. Yeah, in fact, more intense, more easily recognizable than in the occupied part. Yeah.
You use the two inhomogeneous models, means macroscopic and microscopic models. The two models seem to be quite different, totally different, but the results seem to be similar. Can't you distinguish these two models?
You can distinguish these two models, we believe that in our paper we write, with angle resolved spectroscopy. With angle integrated, first of all, I think that real life situation is in between these two extremes. Okay. There is a propensity for chemical compounds to show slight clustering effects. It does happen. Secondly, so it's going to be somewhere in between, not going to be two opposite. Angle integrated spectrum will not distinguish between the two, whereas angle resolved spectrum will, because the dispersions of the various features are very different in the two models. We've stated that, and I hope somebody like Ibra-san will do the angle resolved spectroscopy and will settle the matter somewhere down the line. Because he's just perfectly equipped for that. I saw the beautiful instrument yesterday. But with angle integrated spectroscopy, it's not possible.
Yeah, also on the theoretical side, is it a coincidence or?
That you are similar? No, no. It's not a coincidence. Actually, it turns out to be very similar. See, I say that what is happening is that actually theoretically, it's easy to understand why this is happening. In the macroscopic homogeneity, you have an insulating phase and you have a very slightly doped metallic phase. Okay? One is like lanthanum titanate, the other is like small electron doping in strontium titanate. In the microscopic homogeneity, in the infinite dimensional approximation, again it breaks down into two parts, which is one is exactly like lanthanum titanate, the other is strontium titanate with a difference that now these two are coupled to each other. So that kind of